Welcome to video lecture series on microcontrollers and applications. We are at lecture number 7. In this lecture, we are going to discuss arithmetic instructions of 8051 microcontroller. In previous lecture, we discussed data transfer instructions. We discussed instruction set basics and types, data transfer instructions to access stack, and the data transfer instructions to access program memory and external data memory. Coming to lecture outcomes of this lecture, you may be able to achieve three learning outcomes after completion of this lecture. You may be able to identify and use basic arithmetic instructions in 8051 assembly programming, understand working and how flags are affected by arithmetic operations, apply arithmetic instruction to perform calculations in embedded systems. The first instruction is under arithmetic instruction is the add. Add stands for addition. The syntax is add a comma source. Here the source may be a register, memory, or an immediate number. The operation is it will add a register content with source specified within the instruction, and the result is specified in the stored in the accumulator and carry. Okay, here we are getting 9-bit sum. Okay, when you are performing addition of two 8-bit numbers, the sum size is 9 bits. So here A is not sufficient, that's why carry is used. This carry flag is available in a PSW, program status word. Already you know that the PSW stores the status of the processor. That means it holds carry flag, auxiliary carry flag, parity flag, and overflow flag. Okay, these are the four flags which will indicate the status of the processor after execution of every arithmetic instruction. And one more important thing here, if you observe here, for all arithmetic and logical operation, accumulator is the destination. Accumulator is the destination. So that's why the controller is called as accumulator based microcontroller. Let us see one example here. Let us consider A register is having FFH, B register is the source is having this source is having 11H. Then you can see, if you observe here, we are getting the result in accumulator, 8-bit result. So what is our 8-bit result? You can see after addition you are getting 10H is the 8-bit result. Here's, if you observe here, the 9th bit information is stored in the carry. The 9th bit information is 8 bits are stored in accumulator. The 9th bit sum is stored in carry. And one more important thing, already we know that after every operation, the flags may be set to 1, reset to 0 based on the input or based on the type of operation. So here auxiliary carry flag is also set to 1. Why? Because here after nibble there is a carry. That means auxiliary carry flag will be set to 1. And in this case, the parity is also 1. Why? Because the 8051 microcontroller follows the odd parity. So that means whenever the result is having means A register is having odd number of ones in the result. Odd number means here number of ones in the A register. How many number is the available here? 1. 1 is nothing but 1 is nothing but odd number. So whenever odd number of ones is equal to 1, this parity will be equal to 1. Then similarly overflow flag. but overflow is 0 here. Why? Because as per the definition of overflow flag, there should be a carry from 7th bit position to 8th bit position, or or there is a carry from MSB to carry. But in our example, both are came at a time. So that means here we are having R only. Any one of the condition is satisfied, but here both are satisfied. That means overflow will be 0. Next instruction is the ADDC. ADDC stands for addition with carry. The syntax is similar to add ADDC a comma source. Here the source may be register, memory, or any immediate number. The operation is also similar. Here the only difference is it is also adds previous carry. Along with source, it will also adds previous carry. The main application of this ADDC instruction is it is used when you are multiplying multi-byte numbers. Multi-byte numbers. When you are adding multi-byte numbers, the carry should be propagated to next addition. So that's why this ADDC will be used. This is the one of the application of ADDC. The result is here also stored in accumulator and carry only. Similarly, after execution of this instruction also, all status flags will be updated based on the result. Based on the result, here also carry, auxiliary carry, and parity and overflow flag will be updated based on the result. Based on the result in accumulator. Okay. Then increment. INC. Mnemonic is INC. The expansion is increment. The syntax is increment destination. Here destination may be register or memory. Here the example is increment R0. Increment R0. Let us consider the R0 is having 44H before execution. If we execute this increment R0 instruction, the R0 register content is incremented by 1. That means R0 will get 45H. Similarly, increment 50H. In this case, the content available in 50H memory location is incremented by 1. Let us consider this is 50H memory location of RAM, internal RAM. Let us consider here 34H is available. If I execute increment R0, though, so the content available in the memory location is incremented by 1. That means after execution, this 34 will become incremented by 1. So that means 34 is stored in 50H location. And similarly, INC at the rate R0. Here, instead of representing direct memory, here we are represented indirect memory. So indirectly memory is represented. Let us consider R0 is having 50. So same operation here, but the representation is different. So this is the increment instruction. Then subtraction with borrow. The subtraction with borrow instruction is used to perform subtraction and subtraction with borrow. Normal subtraction and subtraction with borrow. The syntax is SUBB a comma source. And one more important thing, for addition we are having two mnemonics, ADC and ADDC. ADC for addition and ADDC for addition with carry. But in case of subtraction, only we are using single mnemonic for subtraction as well as subtraction with borrow. Here the source, the syntax is subtract SUBB a comma source. Here the source is register, memory, or any immediate data. The operation is here. The source and previous carry is subtracted from A register and the result is stored in accumulator. If any borrow is required, that is stored in carry. Okay. The operation is very simple here. Source and carry was subtracted from A register and the result is saved in accumulator. If any borrow is required, the carry will be set to 1. This is the operation of subtraction with borrow. But in 8051 microcontroller, there is no subtractor circuitry. So that means it uses only adder circuitry to perform the subtraction. So when it is uses the adder circuitry, it will uses the 2's complement addition. In 2's complement addition, we are following the algorithm like this. So the algorithm, in this algorithm, we are having a 3 steps. The first step, take 2's complement of subrand first, then add it to minuend, then invert the carry. These are the 3 steps followed by 8051 microcontroller to perform subtraction operation using adder circuitry. So let us take with a simple example, consider simple example. We need to subtract 2 minus 1. Okay, we need to subtract 2 from 1. So the obviously the result is minus 1. Result is minus 1. In hexadecimal it is represented with FFH. Okay. Then as per our algorithm, first we need to take the 2's complement of this suprahend. So this is the suprahend, this is minuend. The suprahend should be converted to 2's complement form first. To get the 2's complement, first it should be inverted. So you can see every bit is inverted. To get the 2's complement, we need to again add 1, logic 1. So once it is added, we are getting 2's complement of 2. 2's complement of 2 is minus 2. Minus 2 is represented as in hexadecimal FE. Then this 2's complemented result should be added to minuend 1. So this is our minuend. The 2's complement form is FE. Then the FE is added to, in second case, the FE should be added to this minuend. Once it is added, you are getting this result. And we are getting a carry is equal to 0. But as per our algorithm, we need to invert this carry. Invert this carry. So as you are invert this carry, the carry will become 1. Carry will become 1. So carry is equal to 1 is nothing but this subtraction require a borrow. This subtraction require a borrow. This subtraction requires borrow. This is the result. So after execution of this result also you can verify the flags. Carry is set to 1 and similarly auxiliary carry is also set to 1. Why? Because carry is inverted, auxiliary carry is also inverted. That means carry is auxiliary carry is also 1 and then parity. Here if you observe here, how many number of ones are available we need to verify to get parity. So total 8 ones are there. That means even number of ones are available. But in case of 8051, odd number of ones are there, then only parity is equal to 1. So that means parity flag is equal to 0 here. And one more important thing here, any one of the carry is generated, then only overflow is equal to 1. In this case, overflow is also equal to 0. This is about subtraction instruction. Then DEC, decrement. Decrement destination, where the destination is register or memory. Here decrement R0. decrement 50 and decrement at the rate r. Here, suppose for example, let us consider last example, this one. Let us consider R naught is pointing to a memory location 40H. This memory location is having data of 34H, and here we are executed this instruction decrement at the rate R naught. Means the content available in this location is decremented by 1. That means it will become 33H. Okay. After execution of this instruction, this is decremented by 1. 34 is decremented by 1. So this is about decrement instruction. Then multiplication, MUL. MUL stands for here multiplication. Multiplication. If you observe here, the operands are only A and B, and there is no comma specified in between A B. Why? Because for multiplication instructions, A and B are combinedly used. Okay, A and B are combinedly used. So that's why there is no comma. And one more important thing. So before execution of multiplication instruction, A should have multiplant and B should have multiplier. And once you are multiply these two, the product is available in B and A register. Why? Because when you multiply two 8-bit numbers, the product size is 16 bits. The product size is 16 bits. So that's why B and A combination will be used for multiplication instruction. So let us see the operation now. Here our multipland is available in A, multiplier is available in B. So this instruction will perform multiplication of A and B, and the result 16-bit product is placed in B and A combination. Always the B register should have higher order, higher byte of the product, and A register is having lower byte of the product. Lower byte of the product. Combinedly, it is a 16-bit product or result. 16-bit product or result. And one important thing we need to note down here. Let us consider here A is having 1 1, B is having 22. Then after multiplication instruction, we are getting result is 0 to 42. This 02 will be available in B register, 42 will be available in A register. This is the lower 8 bits and this is upper 8 bits. Always the lower 8 bits are available in A, the upper 8 bits are available in B register. And one important thing we need to note down here, if the B register is having non-zero result after execution of multiplication instruction, B register is having non-zero result. In this example, B register is having 0 to H. That means it is a non-zero result. That means overflow flag will be equal to 1, which is indicating that actually the destination is accumulator only. Normally, for every operation, accumulator is normally destination. But in this case, we are also utilized B. So this indicates that the result is overflowed into B. So that means B is also having some product, valid product. So that information is given through this overflow flag here. Okay. This is about multiplication instruction. Then division, similar to multiplication instruction, division is also combinedly uses the A and B combination. So normally this instruction divides A by B, and the result is given in the form of quotient and remainder. Quotient and remainder. And one more important thing we need to remember here, before execution of this division AB instruction, A register should have dividend, B register should have divisor, and after execution, the quotient will be placed in A register and the remainder is placed in B register. And let us see one example here. A is having 10H, B is having 03H. After division of AB instruction, the result is in the form of quotient and remainder. The quotient is 5, which is placed in A register. The remainder is 1, which is placed in B register. And suppose when you are trying to divide with 0, the divisor is equal to 0. In that case, which will indicated by setting overflow flag bit is equal to 1. Why? Because when you divide with any number with 0, the a by 0 is equal to infinite. So this infinite value we cannot accommodate in A or B. These are result holding registers A and B. So these are finite registers. This is 8-bit wide, this is 8-bit. So that means this infinite value we cannot accommodate in A and B register. So that's where overflow flag will be set to 1. And next, the last instruction is the DAA instruction. Decimal adjust for addition. Actually, this instruction is used to correct the result. Correct the result after performing BCD addition. BCD addition. Okay, let us consider two BCD numbers, 28 and 82. These are the two BCD numbers. I need to add these two numbers by using 8051 microcontroller. So whenever I am adding these two numbers with 8051 microcontroller, I am also expecting my result should be in BCD form. So let us see now. 8 plus 2, 10, carry 1. 9 plus 2, 11, carry 1. So that means 110 I am expecting as BCD result. But when you are performing the same addition by using 8051 microcontroller, which will treat this 28 as 28H, 82 as 82H. So whenever these two are considered as 28 and 82, it's the binary representation of these two numbers are 0010, 1000 in binary, and similarly 1000 and 0010 in binary. So then your controller will add like this binary addition 0101 0101. Actually, you are getting A as in hexadecimal result. But our actual requirement is this BCD format. So that's why after performing this addition, we need to use this DAA for correcting the result. And one more thing you need to observe here, the operand should be available in accumulator only, always. Why? Because after performing the addition, the result is available in accumulator only. So that's why the operand is always accumulator. The default syntax for DAA instruction is DAA. Then how this DAA will correct the result, we will see with the help of this example only. Let us note this BCD result is should be 110. and we are getting hexadecimal result is X result is AAH. Okay, then how this DAA will work and how it will correct the result we will see with the help of the example only. Before that, first we will see what how it will perform the division. Sorry, adjust the result to get the correct BCD representation. Okay, now see, always we need to use this instruction after BCD addition or addition with carry instruction. This instruction first checks the lower nibble is greater than 9 or auxiliary carry equal to 1. Add 011 to the lower 4 bits. Okay. And again, it also checks the higher nibble is greater than 9 or carry flag is equal to 1. Again, it will add 011 to upper nibble, upper 4 bits. Okay. So our result is now 1010 1010 binary format. Okay, this is available in accumulator now. This is available in accumulator. So first our this DA instruction checks the lower 4 bits. The lower 4 bits are greater than 9. So that means it will add 0110 to lower 4 bits only. That means upper 4 bits are as it is. The accumulator contents are now 0, 0 carry 1, 0 carry 1, 0 carry 1. So that means, and here this is 1. This one will becomes 1 now. After this, again the second time this DA instruction checks the higher nibble. Now if you observe this also, higher nibble also greater than 9. So in this case it will add 0110 to higher nibble. Now the lower nibble becomes as it is. This will become 1, 0 carry 1, 0 carry 1, 0 carry 1. So that means now carry flag is having 1 and this is 1 and this is also this is 0. So that means our final sum is available in carry and A. So that is 110, which is equivalent to this BCD. So that means our DAA instruction will convert this result into corresponding BCD number. Corresponding BCD number. This is the one of the instruction which correct the results after BCD addition. So let us see the examples here. In X format, 29 is available, 18 is available. 29 plus 18 is 41. So if you consider this 41, in this case auxiliary carry flag is set to 1. Okay, here 8 plus 9 means here carry flag is set to 1. Auxiliary carry flag is set to 1. Actually, this is not greater than 9. The lower nibble is not greater than 9, but auxiliary carry is set to 1. That's why we need to add 06 to the result. So once 06 is added, it is 47. Okay. So in this way, we will correct the result by using DA instruction after execution of BCD addition. In this session, we discussed following key topics: syntax of arithmetic instructions, second, working of arithmetic instructions, applications of arithmetic instructions. Next class, we will discuss logical instructions, how they helps to make the decisions, mask bits, and control the hardware conditions efficiently. And today code is in embedded systems, arithmetic instructions are not just about the numbers. They are how a microcontroller makes real world decisions, one calculation at a time. Thank you.